Okay, our last set of notes was on making a graph right here, and we're going to be referring to this as we go through this lesson. So you're going to want to make sure that you have that handy. Now we're going to talk about how to properly read a graph. Now you've made graphs, like I said, for probably about 6, 7, 8 years at this point. Reading a graph in the way that we're going to do it is probably something you haven't quite ever done yet. Maybe you've done some of it, but we're going to do it's going to be a lot more in depth now. Not that it's going to be hard. There's going to be some challenging parts, but we're going to discover some really interesting things about graphs and how they make our lives and jobs easier. So, to start off, for reading a graph, let's take the equation from our temperature versus time graph, the equation of the best fit line. And I should point out that depending on how you drew your line of best fit, you're going to get something slightly different from this than me. If you actually go through and measure your actual slope, you should see that in y-intercept. It probably is very close to this, but it's probably not exactly the same. And that's absolutely fine, okay? Everyone's going to draw slightly different lines of best fit. But for the purpose of this, what we're going to do is go with the slope, or the equation for line of best fit that I found, which was this. Y equals 8.21 degrees Celsius per minute, x plus 18 degrees Celsius. Okay, so again, you can have your own, but we're going to use this for this example. Best fit lines and their equations are essentially what they are models. Okay, they're very simple models of a system, and they can be used to predict future conditions or to fill in data that we didn't directly take. That's all a model is. It's a description of a system that allows for predictions and extrapolations. When we find an equation, a line of best fit, it's very useful sometimes to replace x and y with the variables that we're actually measuring that go on each axis. So if we do this, our equation will look like this instead. Remember, our y-axis was really temperature, and our x-axis was really time. So I'm going to label this like this. Big T for temperature. Temperature equals 8.21 degrees Celsius per minute multiplied by little t for time plus 18 degrees Celsius. Okay, so this is time and this is temp. Now you can see that this actually makes a little bit more sense. What the model tells us is it predicts the temperature given a certain time, and this should reflect our data. We're going to talk about a bunch of different parts of this equation. Let's start by talking about the y-intercept. According to the chart, the data that we filled out, what is the temperature at the beginning of the experiment? At time t equals 0, it was 18 degrees Celsius. Okay? According to our best fit line in our equation, what is the temperature at the beginning of the experiment? That would be when t equals 0. So if if t equals 0, this term would cancel out. I would have 18 degrees Celsius. And again, that's what we found on here. So in this case, the y-intercept matched up with our data, but does it have to? Okay? A lot of times it will, or at the very least it'll be very close, but the y-intercept does not necessarily have to match your data exactly. Okay? Not at all. And as a matter of fact, all of your data points don't have to match the model exactly, and as a matter of fact, there's no way that they will. Okay? Before we get to that, let's talk about what the y-intercept tells us. It tells us the initial value of the y variable according to our model. Okay? Remember, our model is based on the data points, but the model isn't the data points itself. The model is based on the data points. It allows us to predict and extrapolate places that we don't quite have data. All right? Now, the first time I ever tried this, I didn't have the exact same y-intercept as the data point. And so that's why I wrote this. Numbers above aren't exactly equal, but they're close. They're really close, okay? That's the whole point. Matter of fact, if you look at the data throughout, some of that data, the data points, don't lie exactly on our line of best fit, and that's absolutely fine. The model isn't meant to predict exactly what happens. It's meant to get us pretty close to what happens, okay? Look, there's data points here, here that are above the line, or well, just not on the line. Some are above, some are below, okay? The numbers aren't exactly equal, but they're close. Models are not perfect, but through constant study and refining your data, they become more and more accurate. This one is fairly accurate already. That line of best fit is pretty close to our data. Models can smooth out some of the inaccuracies and errors that arise during measurement, okay? There's some inaccuracies and errors that you just can't avoid. Measurement uncertainty and random error, for instance. What a model does, what a line of best fit does, is it smooths out some of that variation so that we get something that can be useful. Let's talk about the slope, because that's the other important part of the equation besides the variables and the y-intercept. Any 2 points on the best fit line will give you the same slope. They could be really close to each other or they could be really far away. The point is they have to come from the line of best fit. It wouldn't make any sense if I used this point and this point, which aren't on the line, to find the slope, because, well, those points aren't on my line. They're not, they won't have the same slope. I would have to draw a different line to connect those 2 points. You can use data points that are on the line, but I prefer not to. You want to pick data points that are not on the, or you want to pick places that are not data points, but they have to be on the actual line. Okay? The slope is not just a number to be calculated. It's not just something that math people dreamed up somewhere and are like, okay, figure this out. It is something that actually has some significance. For any line, the slope will tell us how the y variable changes as the x variable changes. And you need to keep that in mind. Anytime we talk about the slope of a graph, you're looking at how the y variable changes in response to some change in the x variable. So for this graph, we have temperature versus time. The slope tells us how the y variable changes as the x variable changes, or in other words, how temperature changes over time. So the slope of the temperature versus time graph tells us how much the temperature changes over time. Or in this case, you could even say how much temperature changes per minute, since we're measuring the temperature in minutes. Now, based on the data points, remember, our slope was 8.21 degrees Celsius per minute. Remember, the units are y units over x units. 8.21. Does that mean that the temperature changed exactly 8.21 degrees per minute? No. Matter of fact, it never changed 8.21 degrees per minute. It changed 8, and then it changed 7, 7, 5, 8, 9, 9, 8, 7, 9. It never changed 8.21, but on average, it changed this much, okay? Did it ever change exactly by this amount? No, but it changed about this much on average. So we're looking at the slope as not just some number that we calculate, but as a rate of change, an average rate of change over this time period. That's not something that you necessarily would have thought to find just by looking at this table here, this chart. A lot of times what the slope will represent in this class is a third important measurable quantity that is related to the x and y variables, but it's really hard to measure, okay? It's a lot harder to measure how much the temperature changes per minute or the rate of temperature change, the rate of heating, unless you have a graph like this. I mean, it would be really annoying to find all the differences here and then take the average. Instead, we can we can illustrate this better by making a graph, drawing a best fit line so that people have a visual clue as to what's going on, and then finding the slope. Okay? So being able to graph data and find the slope is a really, really powerful tool. We're going to use it a ton this year. Okay? We're going to come back to slopes a lot. All right? So you need to understand right now that finding the slope is something you're going to do a lot, and finding the slope often shows you something that you would not have been able to find otherwise. Let's talk a little bit about making predictions. We can use the equations that we come up with of the best fit line to predict what would happen in different circumstances that our data didn't capture. So, for example, based on our model, what does the model predict the temperature of the liquid will be after 14 minutes? Well, my equation was T equals 8.21 degrees Celsius per minute multiplied by the time plus 18 degrees. What would the temperature be, big T, after 14 minutes? 14 minutes is the time. I can plug that in for T right here. And I can solve. Order of operations tells me that I have to do the multiplication first, so 8.21 times 14 plus 18, and I have that my model predicts that the temperature should be 132.94 degrees Celsius after 14 minutes. Now, do I have data to back that up? No, but that's the point of a model. You can use it to make predictions, and then you can see if that's actually accurate. Notice also that I used units, and every number that gets them, I wrote the original equation first, then I plugged in with units, then I solved, and the final answer has units on it. So not only can I predict something that didn't necessarily occur, I can also look and measure data points that, we might have data points around it, but we didn't get data points right in the middle of them. Based on our model, what was the temperature after 7.5 minutes? I can do a similar thing. Let me write my full equation first, 8.21 degrees Celsius per minute times T plus 18 degrees Celsius. I never got a data point for 7.5 minutes, but I can reasonably predict it should be somewhere between 71 and 79. I'm going to plug in 7.5 for time, minutes for time, and we're going to see what we get. $61.575 plus 18, and I get 79.575 degrees Celsius. So, something a little funny happened here. I see that at 7.5 minutes, I'm predicting 79 degrees, but then at 8 minutes, it's a little over 79 degrees. At 8 minutes, it's back down to 79. Now, that might show me that, hey, my model might not be quite accurate, okay? I mean, at least it doesn't say it's 100, or it doesn't say it's like 20, but something might be a little bit off. Maybe I drew my slope a little bit too steep. Maybe I had a miscalculation here. Whatever the case may be, it's cause for further study. Okay, so it's actually good that that's happening because now we can go back and refine our model. But I'm still going to box it in, okay, because that is something, it's a result. I'm not just going to ignore it, I might pay more attention to it later on. Third example, another prediction. After how many minutes would the temperature of the liquid reach 160 degrees Celsius? So this time we're not going to be solving for capital T, the temperature, we're going to be solving for this, little t, the time. 8.21 degrees Celsius per minute multiplied by the time plus 18 degrees Celsius. I plug in 160 degrees for temperature. Don't plug it in for time. You're solving for the time. You plug 160 degrees in where the temperature goes, here. Equals 8.21 times T plus 18. Now to get little t by itself, we're going to have to subtract the 18 over to the other side. That'll give us 142 equals 8.21 T. And then we're going to divide. And we're going to divide each side by 8.21. So the temperature ends up being, the time that it takes for the temperature to reach this temperature, assuming it doesn't boil or anything, is 17.3 minutes. Okay? So we can use our model to make useful predictions. I've got two more things that I want to talk about. One is an analysis tool that is extremely important, just as important as figuring out the slope, but it's not used as much. And it's not used as much in this course, but you still need to know it because it is useful. But it's used a lot more, even more frequently in AP Physics. And that is finding the area under the curve. Every once in a while, finding the area under the curve is useful. You do this by breaking the space under the best fit line up into very basic geometric shapes. And the units must be included when we do this, all right? And we're going to do this, and I'll show you what I mean in just a second. We do this only under the extent of the data points, not the entire best fit line. Because you can extend a best fit line for however long you want. You only find the area under the curve right under the extent of the data points. So it says below, determine the area under the curve for the graph you constructed. Well, here's my graph, and you can see that the area under the curve is this right here. the area between the best fit line and my x-axis. I can break this up into two easy to understand shapes. I can break this up into a rectangle, okay, a rectangle and a triangle. And since my data points go from one side to the other, we don't have to worry about limiting our areas on the curve. This is our limits. All right, so I'm just going to find the area of this triangle and this rectangle. You learned the area formulas years ago. They're very simple to use. So let's find the area of the rectangle. First, we know the area formula for a rectangle is base times height. The area of a rectangle, let's see, so base times height, let's see, our base, and we're going to make sure to use units, I'm going to say our base is this side right here, down here. Now, how wide is that base? I'd say it's 10 minutes wide. So I'm going to write down for my base 10 minutes. And the height goes from 0 up to about 18 or so. So I'm going to call the height times 18. And what were the units on that? Degrees Celsius. So we're not measuring the actual height or width. We're not taking, like, let's say this ruler and putting this down here and measuring in inches or centimeters. We're measuring using the units along the axis itself, okay? So the area of this rectangle is 10 minutes times 18 degrees Celsius. 10 times 18 is 180. So it's 180 degrees Celsius times minutes. The area formula for a triangle, the other shape that we have to do, is 1/2 base times height. 1/2. The base of this triangle, you could also say, is 10 minutes. I know it sounds weird to say a base, to measure a base in units that aren't meters or feet or whatever, but this is how it's done, okay? We're not measuring the actual size of the triangle, we're measuring the size on the graph. So that's 10 minutes. And the height, don't get messed up by this one, this can be a little tricky. The height goes from here to here. The height goes from 18 to this crosses right here at about, I'm going to say it's 93. So it's 93 minus 18 is 75. So the height is about 75 degrees Celsius. So the area of this triangle is 1/2 times 10 times 75, which is 375. And again, the units are in degrees Celsius times meters. Just because it sounds weird doesn't mean the units aren't right. We're multiplying these numbers together, so the units get multiplied as well. 375 degrees Celsius times minutes. So the units are, I'm going to write this down, x units times the y units. Okay? Now to find the total area, we simply add those areas together. AT plus AR equals A total. Triangle is 375 degrees Celsius times minute plus 180 degrees Celsius times minutes. Sorry for my bad planning there. 375 plus 180 is 555 degrees Celsius times minutes. Now, what the heck is a degree Celsius times a minute? Why is this important? In this case, it's not. Okay? Sometimes the area under the curve gives no useful data. Sometimes it will. This happens to give us no useful data. All right? The slope of a best fit line will always tell us something useful. Area under the curve often gives useful data. Okay? So you got to keep that one in your back pocket because it will show up sooner rather than later in an important sense. Let's end by talking very quickly about graph shapes. Just by looking at the trend of a graph, you should be able to get what is happening and describe it and answer some basic questions about it. You should always ask yourself these 3 questions when you look at a graph for the first time. First question is, as the x variable increases or moves to the right on the graph, what happens to the y variable? Does it increase, decrease, or stay the same? This is the same thing as asking if the slope is positive, negative, or 0. So let's answer this for this first one right here. As x, this is my symbol for increases, as x goes up, what happens to y? Well, nothing. The y variable doesn't go up or down. It stays at the same level. So I'm going to say y stays the same. That's my symbol for stays the same. okay? This is the same. If I say y doesn't change, that's the same as saying that there's a slope of 0. If I were to measure the slope, change in y over change in x, the change in y is 0. Here, on the other hand, I'm going to get a positive slope, the y increases. Here I'm going to get a negative slope, the y decreases. Let's look at the second question. Is the slope constant, or does it increase or decrease? This slope, the steepness, remember, slope just means steepness. This steepness is constant, so I'm going to say that this is a constant slope. And lastly, the third question you should always ask is, does the y variable start at 0, or does it have some initial value? Here, very clearly, 0 would be down here at the x-axis. It is not starting there. So I'm going to say b, using the symbol for y-axis, or y-intercept, is not 0. I'm going to fill this in for all of these graphs, and I would take a second right now to draw these graphs on yours, so that, and think about what your answers would be to all these questions. There's 7 that we're going to go over. Okay, so this next graph. As the x variable increases, what happens to the y variable? As x increases here, I would say the y also increases. We go from low to high. Y increases going up, just like on all graphs, so we say the y is increasing as well. This is the same as saying it has a positive slope. The value of the slope is positive. Again, is the slope constant, or does it increase or decrease? Even though the slope is positive and the points are going upwards, the steepness does not change. This is the same steepness the whole time. So if it's the same steepness, that means it must be a constant slope. And finally, this does start at 0. So the y-intercept is 0 for this one. Next, as x increases, the y variable decreases. For low x's, y is high. For higher x's, y is lower. So as x increases, y decreases. This is the same as saying the slope is negative. But again, the steepness of the slope does not change. So this is still a constant slope. Don't call this a decreasing slope. This is constant. Constant and decreasing have opposite meanings. They're not the same thing. When you're looking to say if the slope changes or not, think about if it's constant or not. And again, the y-intercept in this case, since it doesn't start at 0, we're going to say b is not equal to 0. For the fourth one, as x increases, y seems to tend to increase. Now here we actually have a slope that's changing. The steepness changes from something that's not very steep to something that's very steep. So I'm going to say the slope increases. And again, the y-intercept is not 0. Depending on what these variables are, we might have more to discuss, okay, once we know what the slope tells us, once we know what these variables are. But for right now, you should just get in the habit of looking and seeing, okay, what is happening to the y variable as x increases? What is the slope doing? Is it changing or is it constant? And what is the y-intercept? For this one, I would again say as x increases, y increases. But look at that slope. It's definitely a changing slope. It's not the same steepness. It starts off very steep, becomes not that steep. So I'm going to say that the slope goes down. And again here, the y-intercept is 0. For the fifth one, as x increases, y decreases. In the slope, it's kind of tricky to describe the slope here because it starts off with a steep slope and then it's not steep. But I'm not sure I would say it decreases because the slope is negative and then becomes less negative. We know that the slope is negative here, and well, it's negative the whole time, but we know it's more negative here because it's more steeply angled down. So what I'm going to say here is just the slope is now smaller as it goes on, closer to 0. And this obviously is y-intercept is not 0. For the last one, again, we have as x increases, y decreases. And if you're looking, the slope starts off kind of shallow, becomes very steep at the end. So I'm going to say that the slope becomes larger. The value of the slope, the steepness, becomes larger. And again, b is not equal to 0. We're going to look at tons of graphs this year, and you're going to see shapes that are very similar to these. Okay? I just wanted to give you an overview. Just wanted to give you an overview of graph shapes and get you kind of thinking about how what you should do when you see a graph. You don't panic, you immediately go to these questions, and that'll help you to start analyzing what the graph says. So that's the features of a graph that you need to know how to learn or how to read: area under the curve, slope, y-intercept, using models to make predictions. we're very close to getting into the actual physics content, which is good. I'll see you very soon.